So, we'll start on with our discussion with regards to protein stability curves. So, I'll go through a brief recap of what we were doing last time. So, we defined the stability curve as essentially the dependence of free energy on temperature, and whatever we are looking at is this free energy of denaturation, where D stands for denatured, N for native, and we are looking at the difference in free energies between the denatured and the native state. We looked at this stability curve for a protein, and one of the major points in this case was if you would compare it with the stability curve or with the free energy curve of a hydrophobic molecule being dissolved in water, then you would see the difference being that TH and TS are very near to each other in this case for a protein. However, for a hydrophobic molecule like neopentane, this TH and TS were far apart from each other, right. Now, there are a couple more points in this case. For example, if you would look at the stability curve, which is this plot of again delta G versus temperature, there are 2 points at which the stability curve cut the 0 line. So, this is the 0 line. So, this is the 0 line. So, there are 2 points. So, when delta G is equal to 0, it is essentially that means K is equal to 1, K equilibrium is equal to 1. What it means is that you have equal concentration or equal number of unfolded molecules and folded molecules, right, and that is referred to as the midpoint of any transition. What I refer to what I mean by midpoint will be more clear in just a few minutes, but the more important thing is that see there are 2 points. One is we know that when we heat a protein up, it has to denature. That means you destroy all the all the stabilizing interactions and you start opening up. So, one of those points is Tg, which is the heat induced, that means the increase in the temperature. But what possibly we did not realize was that if you would also decrease the temperature, a point would come where the protein will again denature, right. So, that means a point will come where K is equal to 1 again. So, that is your Tg prime, which is the cold denaturation point. I have written midpoint again for a specific reason, because whenever we are talking about Tg and Tg prime, these are essentially midpoints of certain transitions we are looking at, and it will become more clear in the next few slides. And then we had looked at these thermodynamic relations before, and these are some of the relations we are going to go on using quite often. So, one more thing was the curvature. It is you can see the curvature depends upon delta Cp, and the slope of the curve is given by delta S, and it is needless to say that where the slope of the curve is the maximum, this is typically here, what happens is then delta S should be equal to 0. That means the slope of the curve corresponds to that temperature where it is delta S equal to 0, that means Ts. So, that is what we refer to. So, just by another diagram which we are going to come very soon. So, one of the properties or one of the assumptions was that the native protein is assumed to be stable in a certain range of temperature. Hence, delta G for unfolding will be positive in that temperature range, because in that temperature range what we are assuming is that the folded state is more stable, and if you are trying to unfold it, that means you are doing a process which is non spontaneous, and hence delta G has to be positive. Next is, as we said, that stability curve crosses at 2 points. One corresponds to the high temperature melting point, the other one corresponding to the low temperature melting point, right. So, this is again the triangular relationship which we were talking about. So, you can see that here the maximum stability corresponds to Ts, right, and the triangular relationship is between Ts, Th and delta G. So, there are 3, right. It is being referred to by a triangle of this form, and that is why it is called a triangular relationship. But I guess the take home point of this one was why Th and Ts are very close to each other for a protein, and what we finally decided on, or what we looked at, was that this Ts minus Th is given by this what we derived is given by the dependence of or the ratio of delta Gs and delta Cp. Now, it is called delta Gs because it is delta G at that temperature of what is corresponding to S, right, the Ts. Now, what it means is therefore delta Cp for unfolding is large and falls in the range of 12 to 18 calories per degree per residue. Now, this is definitely an approximation, but think about it. If you have a number like this, it is 12 to 18 calories per degree per residue, right. Now, given a protein, it can have 100, 200, 300, 400, many residues. See, even without actually doing a formal measurement of delta Cp, what you can gauge is, or right, at least you can estimate based on this, what is the possible delta Cp you are going to see, right, because you are already given the range. It has to be between 12 to 18 calories per degree per residue, and depending upon the number of residues, you can multiply it by that number. I can see, okay, this is supposedly my delta Cp change. That is theoretical. Well, theoretical means it is an empirical observation. It is an observation, I should not say empirical, it is an observation based on experiments. You take this and you compare with what delta Cp you get from doing measurements. Once you do measurements, you get delta Cp, you have this value, you can compare, you will see they are oftentimes very close to each other. So, it is a very good guess. Well, the other point is, the maximum stability of the protein ranges between 50 to 100 calories per residue, and this is not too high, this is really not too high, and hence, because this ratio of delta Gs by delta Cp is small, which means that Ts minus Th, the difference would be small, and thus for a protein they lie very close to each other. Okay. So, what we will do now essentially is, this was your recap. So, we will start from here, and before looking at thermodynamic unfolding, we will do some more thermodynamics based on what we have learned. So, let us again start from the very basics. So, what I would write here is some more thermodynamics. Okay. So, what we know from before is this, we know. Here what we will do is we will take the reference temperature. We will take the reference temperature as Tg. Remember what is Tg? Tg is our heat denaturation point, right, where delta G goes to 0 on heating. And then what we had is, we had this delta H T was equal to delta H T1 plus delta Cp T minus T1, that is what we had from before. So, what we said was, I am just rewriting it because it will help us in kind of maintaining the continuity. We will say that T1 is equal to Tg, and then what we will also write is, what will you write here? We will write T is equal to what? Th, right, T is equal to Th, because we know at Th delta H goes to 0. So, based on that, what we can write is delta H T of H is equal to delta H T of G plus delta Cp T of H minus T of G, right. And here this delta H T of H goes to 0 by definition. Okay. Delta H T of G we will write as delta H G. We will just not write T of G all the time, we will just write as abbreviated as G. Okay. And from here what we got was this relation delta Cp Th minus T of G is equal to minus delta H G, or Tg minus T of H is equal to delta H G over delta Cp. And I forgot what was the number of this equation. I think it was 2, if I remember correctly, right. Okay. So, we have this. Now, see what is the beauty of this relation or this equation is, it relates your Tg, which is the midpoint of your transition, to Th through the ratio of delta H over delta Cp. Okay. That means, if you are not knowing Th, but you will be knowing Tg, I will tell you how to find that, it is easy to find, and if you can measure delta H and delta Cp, then you can find Th, right. So, what we can do here, we can rewrite this equation as saying that therefore, Th is equal to Tg minus delta Hg over delta Cp. So, this is our equation number 3. So, this is the relation between Th and Tg through the ratio of delta H over delta Cp. Okay. Now, correspondingly what we will also do is, we will do the same for entropy now. So, let us look at entropy now. So, again delta S of T was equal to delta S, here I think we had written T 2, then plus delta C p natural log T over T 2. And since we have said that the reference temperature T 2 is equal to what? T g, and we also say that T is equal to what? T s, because delta S of T s is equal to 0. Then we write delta S of T s is equal to delta S T of g plus delta C p natural log T s over T of g. Okay. Now, by definition delta S T s is what? Equal to 0, and then we can abbreviate delta S T g by delta S g, right. So, these we are done before, right, and we can rewrite this equation as delta S, well T of g, I wrote it again anyway, is equal to minus delta C p natural log T of S over T of g, or natural log T of g of T of S is equal to delta S g over delta C p. What was the number of this equation? I think it was 3, okay, because I have to maintain the equation sequence. Now, what I will do is I will do a small change. If you go back to the previous slide or the previous thing we wrote, this 3 what I will change to is this 3 what I will change to is 6. Okay. So, this one is not 3, this one is 6, because I think last time we did 5 equation number 5. So, we will start with 6 here. This is a kind of a new equation we wrote down, and this is 3 essentially for you. Okay. So, from here now we will go forward. So, this we have not done, then I can write T g by T of S is equal to e to the power delta S g by delta C p, right. I can write this too. See, I have to simplify it. I have to get a very simple relation between T g and T s, because last time what we last time is just before this, the equation number 6 was a relation between T h and T g. So, we need a relation between T s and T g. Okay. So, what we will do is we will do an expansion, that means expand e to the power delta S g delta C p in series form, okay. And once we do that, what we will have is T of g over T of s is equal to, what is the expansion? 1 plus delta S g over delta C p, and that is what we will stop. We will not go to the higher orders, because we are doing it for a very small number x, which is delta S over delta C p. Then accordingly what we can say is, therefore, T s is equal to what? We are getting a relation between T s and T g is T g over 1 plus delta S g over delta C p. Okay. But that is not the end of it, we can simplify it further. How can we simplify it further? The way we can simplify it is, remember what is delta S g? Delta S g means the change in entropy at the transition point T g, is not it? Now, at the transition point T g, what is delta g? 0. So, essentially at T of g, right, delta g at T of g, delta g is equal to delta H g minus T delta S g, right, and because at T of g delta g is equal to 0, because of T of g delta g is equal to 0, this is our denaturation midpoint, or the place where it cuts the axis at delta g is equal to 0. We can write delta S of g is equal to what? Delta S of g is equal to delta H g by T, and here the temperature being what? T g. Very good. So, this we know. So, what we will do is we will take this and plug it back into the equation to get T of S is equal to T of g, then 1 plus delta H g by T g times delta C p. Okay. So, this is another relation we can have. Now, once we have this, what is the further simplification we can do? Remember, what I am trying to do is, here I am trying to express Ts in forms of essentially in form of Tg, okay, and another temperature which is Th. How can I bring that in? What do you think? What is delta H over delta Hg over delta Cp? Huh? Tg minus Th. Okay. So, what I can then replace it by is Ts is equal to T of G 1 plus Tg minus T of H over T of G, okay, because I know what delta H by delta Cp is. So, I can write from previously derived. What was equation number? It was 2, wasn't it? Huh? Yeah, it was 6 2 is the same. So, from previously derived equation 2, okay, and then we further simplify it. So, when we further simplify it, what do we get? We get on the numerator we get Tg squared, and what do we get on the denominator? 2 Tg minus Th. So, this we can write as, say, equation number, let us say we write as equation number 7. Okay. This can be written in another form. So, you can see we already have a relation between the 3 temperatures, Ts, Th and Tg. That means, you know either of these 2, you get the third one, right, and there is also a very simple relation between Th and Tg, which is delta H over delta Cp. So, you see all these are very much interconnected. Okay, once we have this, this can be written in another form. I will just give you the form because I have it with me. It is essentially just for the simplification. So, the way people finally express this Ts is as T of H, okay, plus Tg minus T of H whole squared over 2 of Tg minus T of H, and just further simplification from equation 7, and let this be equation 8. So, again it gives you a relation between these 3 characteristic temperatures, Ts where delta S is equal to 0, Th where delta H is equal to 0, and Tg where delta G is equal to 0. You can see these are huge, the impact is huge, right. You are talking about 3 very fundamental thermodynamic parameters. Okay. So, that was this. Now, see, you have one more thing coming in. What we know is that delta G, if we talk about the free energy at any given temperature, is equal to delta H minus T delta S at any given temperature. Okay. So, I can rewrite it as delta G at any given temperature is equal to delta H of T minus T delta S at a certain temperature. This is your Gibbs-Helmholtz equation. Now, from here where do we go? From here what we do is we have a relation, we know what delta Ht is, we also know what delta S of T is, okay, in terms of Tg and T. So, that means what I can write is delta G of T is equal to, what was delta Ht for me? It was delta H, if I keep the reference temperature as Tg, it would be T of G, right, plus delta Cp T minus Tg, that is your delta H as a function of temperature, right, minus T, then what do you have? Delta S. So, delta S I can have it for Tg plus delta Cp natural log T over T of G. So, what we just did here is we just replaced the corresponding temperature dependencies of delta H and delta S. You are following up to this point, right. Now, you can simplify it. How can I simplify it? That means, you take this and just rewrite it, so that it becomes a little more clear. So, I can have delta G of T is equal to delta H Tg I will replace by G, right. Then I will write minus T delta S G, okay. Then I can write plus delta Cp, I will combine the other two, I can write T minus T g, then what should I write? Minus natural log T by T g. So, what have we done now? What have we done is you have now expressed delta g in terms of what? Delta H, delta S, g, this temperature you know, but as a function of another temperature T which you do not know. Okay. Now, can this portion be simplified, the first two terms, can this be simplified further? What happens? Well, it is del g, yeah, okay, it is del g, that is fine. So, now what I can do is, what is delta S g equal to at g, T g? No, delta S g, what is delta S g equal to? Okay, good. So, therefore, delta g of T is equal to delta H g minus T times delta H g over T of g plus delta C p T minus T of g minus ln T by T of g. Okay. So, I can rewrite this delta g of T as equal to delta H g 1 minus T over T g plus delta C p, then I will just open brackets T minus T g minus natural log T over T of g. So, this final equation, is often referred to, so this final equation is often referred to, I will write the name, it is often referred to as a modified Gibbs Helmholtz equation. So, this final equation is often referred to as a modified Gibbs Helmholtz equation. Now, see the essence of this equation. What you are doing is you are expressing the free energy as a function of temperature, right? By what terms? One is obviously T of g, but there are two other very characteristic terms. What is? One is delta H g and the other one is delta C p. Now, why are these so important? These are so important because both of these can be measured experimentally, and hence if you can measure these experimentally, right, then what you can get? You can get the value of delta g, free energy change at each and every what? Temperature. So, that is the beauty of this equation. See, you have removed delta S, right? You removed delta S from the condition was what? That at T of g delta g should be equal to 0. So, therefore, delta H g must be equal to T g times delta S g, right. Just to make the take the point a little further, this equation which we just derived is almost all the time or very often used by biophysical chemists to extract thermodynamic parameters from protein unfolding transitions, and that is why this equation is so important for people doing that kind of research or that kind of work, and that is why it is not your exact Gibbs Helmholtz equation, it just says it is a modified Gibbs Helmholtz equation. Okay. But see, what we have done here is we have looked essentially at T of g. What about T g prime? What about T g prime? This is our cold denaturation temperature. So, T g prime is a cold denaturation temperature. Okay. So, what in this case, you know what you can do is, what will you do? What will you do is to find T g prime. Can you do it from this equation? To find T g prime, can you do it from this equation? How would you do it? Remember, I am trying to find an expression for T g prime. This equation, no, I will not do that, because I know T g. I will not try to replace T g. What will I try to replace? I will replace T. the moment I replace t by t g prime, what do I get? I get delta g t g prime is equal to 0, because that is the other point, and the moment I get that 0, I have the other equation coming in. Okay. So, what I do is, in this equation, what I do is, let t in the equation we just derived, let that be equation. So, what should the equation number be? 9. Okay, let this be equation number 9, let this be equation number 9. Okay. So, in this equation, let t equal to t g prime in equation 9. So, the moment we have t is equal to t g prime, so what we can write is delta g t g prime is equal to 0, is not it, and hence 0 is equal to delta h g 1 minus t g prime over t of g plus delta c p t minus t of g, where t is t g prime minus natural log t g prime over t of g. Okay. And this equation has to be simplified further to get t g prime, but the problem is that you have a certain factor or a certain term which is what, which will actually hamper your simplification. It is the natural log of t g prime over t g. See, everything else is very straightforward. So, this is a homework for you. The homework for you is to prove or to get the final expression for t g prime, but so the final expression for t g prime is, so final expression, I will give you the final expression for t g prime is, give you the expression, t g prime is equal to, so t g prime is equal to t g squared by 2 delta h g delta c p plus t of g. Now, this is the final expression for t g prime. I will give you a hint how to do it, I will just give a small hint. So, you just have to go through the algebra, but first try to realize the inherent meaning of this equation. See, cold denaturation temperatures are not very easy to find. The reason being, it often happens that T g prime is well below 0 degree Celsius, and hence either you have to change the solvent condition or do something else to go to that cold denaturation point. But if you have a relation between T g prime and T g, at least you would be knowing, because it is easy to find out T g, you would be knowing where T g prime would come in, because you would know what, you would know T g and you would know delta H g and delta C p, right. Now, tell me, how can T g prime be increased based on this equation only? That means, my T g prime I am telling you is already very low. How can T g prime be increased? That means, it comes more in the measurable range, that means kind of close to room temperature or even 5 degrees, 10 degrees. How can we do that? You look at the numerator, what does the numerator have? The numerator has this delta H g over delta C p, right. What happens if delta H g is small and delta C p is big? What will you get? So, the question is, if delta H g, that means if based on equation 10 delta H g is small, based on equation 10 delta H g is small and delta C p is large. Okay. Huh? Yeah. So, well, we are not saying it is very small, but I am saying that the ratio is small. You are absolutely right. So, if you look at this, if this ratio is small, what will happen? Then the denominator will approximate to T g, say, and then you have T g square, that means T g prime would approximate to what? T g. In other words, what are you doing? You cannot have T g prime equal to T g, essentially they are on top of each other, then there is no T g or T g prime separately. But what you are saying is that if my ratio is small, then what can happen? T g prime can tend towards T g, that means tend to go higher up, and you can bring it within the room temperature, within the observable range, not far below 0. Is it clear? So, that means if my delta H is my change in enthalpy is low, if my change in Cp, that means delta Cp is high, then I can have a condition, which can give rise to Tg prime, which comes within the experimental conditions like above 0, and I can measure it. Okay. So, this is why this equation has extra importance. It tells you what Tg prime, the cold denaturation temperature, depends upon, and knowing Tg, you can actually guess what Tg prime is based on this equation. Okay. So, we have kind of seen two different midpoints or two different points, one is the Tg and one is the Tg prime. What we will mostly focus on in this course is Tg, because it is easy for us to handle. Tg prime, as I said, is always, its window is always not that easy to deal with, and so we will not do that. But I will give you just a small hint at how people try to bring Tg prime higher up. That means, what they do is, if you add say a denaturant like urea, chemical denaturant like urea, if you add a chemical denaturant like urea, what it does is, without going into the details, if you are going to denature anything, what will happen? Delta Cp is going to change huge, but the delta H will be small. If the delta H is small, delta Cp is huge, what you are doing is, you are not only, remember, you are already adding denaturant, that means you are denaturing the protein. So, if there was no denaturant, chemical denaturant, the protein Tg would be having a higher value. That means, it will, Tg means where it unfolds, where concentration unfold is equal to concentration of folded, right. Just hold on, I will come to this. If without urea, Tg was say 50 degrees Celsius. Now, the moment you add urea, a chemical denaturant, that means you are already destabilizing the protein to start with. Okay. So, what will happen to Tg? It will come lower, and remember, because this numerator ratio is small, so Tg will also start, Tg prime will also start going towards Tg, and hence in that case, that is one of the ways, by using a chemical denaturant, that people can bring Tg prime within the experimental window. A very good example is, I will possibly take that example later. A very good example is apomyoglobin. You know what apomyoglobin is? Apomyoglobin is myoglobin where you take out the prosthetic group. See, apomyoglobin is very subjected to I mean it is prone to cold denaturation, and the way you can bring it within the easily within the experimental window, say 20 degrees, 15 degrees, is by adding more and more denaturant, and it is a proven fact. I will show you the data before. I have data in my own lab which I can show you later, but it can be done. It is essentially all thermodynamics for you. Anyway, so the hint which I was trying to give you is this. So, the hint is, so this would be a homework problem. So, hint for deriving the expression for Tg prime is, you use an expression of natural log. So, of Tg prime by T of g, I am giving you the expression for this. So, this is T of g, okay, minus well, T of g prime minus T of g over T of g minus Tg prime minus T of g over 2 T of g. So, this is squared and this is squared. So, this is the approximation you are going to use. This is the approximation you are going to use to find out essentially what your Tg prime is. Okay. So, these were just some more thermodynamic manipulations with the corresponding Th, Ts and Tg. But where are we finally going with this? This is what we want to address. The most important concept of the topic is thermodynamics of protein unfolding. That means if a protein is unfolding, how can we get delta G, delta Cp, delta H, Tm and all these things. Now, what do I mean when I say protein unfolding? Let us talk about protein stability a little bit. Why do we want to measure protein stability? We want to measure protein stability because it provides an understanding of the various forces and energetics involved in determining the native structure of the protein. Okay? See, you take one protein, say a myoglobin, you take another protein, say human serum albumin, and you see that one protein is more stable than the other. The natural thought which comes to your mind is, why is it more stable? Where does the stability come from? And the only way possible you can address it, one of the ways you can address it, you try to denature it and see how hard this one is to denature as compared to the others. And you know that this denaturation midpoint or this transition point where k is equal to 1, Tg is dependent upon this delta Hg and delta Cp. So, immediately once you know Tg, you have an idea of what the delta Hg and delta Cp, these relations, and these are your thermodynamic parameters. And you also know this, when a protein is unfolding, the change in delta Cp is huge. Okay? So, all those things will now hopefully fall in place. Where is it really important? One was this, the other one is, suppose you take a protein and see you take a protein which has 100 odd amino acids, say about 100 amino acids. You are trying to figure out which set of amino acids might be very important to the stability of the protein. So, immediately what will you do? If you are trying to figure out an amino acid's contribution to stability, the best thing for you to do is take that amino acid out and mutate it by or replace it by other amino acid, essentially a mutation. Now, if that amino acid is very is a key unit for the stability of the protein, what will happen? The stability of the protein will say decrease, right? And because the stability of the protein decreases, possibly the protein because it becomes unstable, it will melt or denature more easily, and this corresponding thermodynamics, this corresponding change in stability is essentially your change in free energy, because free energy is the one which finally defines the stability, right. So, this free energy change, with this free energy change you would be able to address whether by doing a certain mutation the protein is become more stable or less stable. It is not always that you put a mutation in, nothing will happen. It can happen, especially if you do a mutation. For example, you see, if you take a protein, where do you think if you do a mutation your protein would be least affected? Where do you think if you do a mutation your protein will be least affected? Where do you think? Will it be the core or will it be the surface? Least affected, not most affected. See, I think it would be the surface, right? Because see, surface you mostly have polar charged residues, right? You have many of those, all those are interacting with water. You can take one polar charged residue out, right? You replace with say a little bit non-polar one, but you have still many other things out there because it is a surface and they are helping you solubilize the protein. So, in that case it might have, but your expectation, immediate expectation would be not that much, right? It may be special case, but not that much. However, you will think about the core is essentially what? Hydrophobic. So, there is a very delicate balance between these forces, it is a packed interior. So, in this there is a reason why different proteins have different amino acids in that core. So, if you would be replacing say one of the hydrophobic amino acids say by a relatively polar amino acid, what would happen? It would immediately destabilize, because your core is essentially what? Hydrophobic, it tries to stay away from water, and hence the delta G would immediately change. Okay. But these were just two extreme examples, and people have done many mutations, and that is essentially how people do to see which amino acid contributes to what extent to a protein structure. Okay. How to study stability? To study stability, one needs to measure the free energy of unfolding of the protein, right. We know what free energy of unfolding is, it is delta G d of n, right, or dn. So, here what we will see is this is delta G dn, it is a different way of expressing it. It is the free energy of the denatured state minus the free energy of the native state. We are also going to look at this. Okay. So, need to perform experiments at equilibrium when unfolding is reversible. Okay. Now, this is important. When you are talking about delta G is equal to 0, delta G has an immediate relation with equilibrium constant minus RT natural log K equilibrium. Now, what it means is, no matter what you do, you have to make sure that the system is always at equilibrium. That is why these are equilibrium measurements. Your system is always at equilibrium. If it is equilibrium, what is the definition of equilibrium? Definition of equilibrium is, you go back to your initial first law of thermodynamics. You are making a change in a system, right? You change the system by a very small amount and you immediately revert the change, then you are going to come back to the same system. You change by very little, right? So, that it is essentially you infinite number of steps, right? And then again you come back, you will retrace the same path. When you talk about reversibility of unfolding, what does it mean? That if you are unfolding the protein by a certain path, now if you once you have unfolded the protein, now if you want to trace back the path, it should essentially what? Superimpose on the path which was traced to the unfolded portion. So, that is what it means by reversibility. So, you went towards the unfolded state and you are coming back from the unfolded to the folded state, essentially following the same path. Okay, that will ensure reversibility. Actually, that is not very easy, especially when you are doing experiments based on temperature changes or as a function of temperature. Okay. But this we will see later. Now, so we are talking about unfolding of a protein. How would you unfold a protein? There are many different ways of doing that, and people have tried typically all these ways. Thermal denaturation, right? Thermal denaturation means you are just taking a protein in a certain solvent, say buffer, and you are heating it up. You do a thermal denaturation, good. Now, you can also do a chemical denaturation, that means instead you keep it at say room temperature, say 25 degrees Celsius, you add denaturants like urea or guanidinium hydrochloride, and these two are the most favored denaturants for people when they do denaturant induced unfolding. So, you can do that. Anything else you can suggest? What should the other one be? This you should be able to tell me. pH, yes, the other one is pH, and we know why pH changes would bring about denaturation. This we have talked about in terms of the charge densities and all these things. Anything else? Salt concentration, okay. There is one more thing. Huh? No, mutation is not your way of denaturation. Mutation is you do a mutation and you see how it has affected the protein stability, right. The other one possibly we will look at is pressure. Your pressure will also actually denature your protein, okay. That means do not be under too much pressure all the time. Anyway, so pressure does induce protein denaturation, and can you quickly tell me how you think about a pressure denaturing a protein? Huh? What denaturation? Osmotic. Okay, explain it to me. No, I am just doing a pressure denaturation. Pressure means I am actually applying pressure. I am actually applying pressure, it is not a osmotic pressure. I am actually literally applying pascals of pressure. Why will the protein denature?
Charge will come closer.
Charge will come closer. But your protein core is already pretty hydrophobic, isn't it? Think. One more chance. Think simple. What do you have in water? What do you have when you take a protein in buffer? Apart from protein, what do you have? You have solvent, right. Now, if you would be putting pressure in, remember a hydrophobic core is devoid of solvent, right. If you would be putting pressure in, if would be pressure, your water concentration is huge. Now, what will happen? The water can actually go inside the hydrophobic core because you are putting pressure, remember. And if the water goes inside the hydrophobic core, what will happen? The protein will denature. That is one of the easiest ways of thinking about protein denaturation, and that is true. If you think about it, what you will think, see, if you would not be thinking about the water part, what you will think is, okay, if I would compress the protein, right, I can compress to a certain extent without changing anything, but if I do a far more compression, what will happen is my London's dispersion forces, repulsive forces will take over and protein will fall apart, essentially, as you said. But that is not the only thing. Remember, when you have a protein in water, you have so many water molecules. What is the concentration of water essentially? 55 molar. That is huge, excellent, that is huge. So, that will go inside, because you are compressing the whole system, right, you are not only compressing protein molecules, and they will denature. So, that is also an interesting way of doing it, but I will tell you what the problem is. The problem is, if you are going to do pressure denaturation, this is high pressure situation. The experimental what should I say, the experimental setup is not so easy to deal with. That is why you need very not modern, I should say, dedicated setups which can handle huge amounts of pressure. Okay. So, in unfolding, what is the main idea? The main idea is that you pot out the equilibrium, and once you pot out the equilibrium, then you determine the fraction of the protein that is unfolded. Okay. So, this is the typical thermal denaturation curve, right. So, look at what we are seeing is, we are looking at two proteins, one is ribonuclease A and the other one is myoglobin. Now, what is Tm? Tm is essentially equal to T of G. Tm is essentially equal to T of G. So, where does M come from? M comes from either melting or the midpoint of the change. Now, what change are we talking about? Okay. So, what is Y? I will tell you what Y is later, but Y essentially is an observable. That means, you are changing the temperature, right, by some way or the other, and then you are seeing a change in the signal Y, unobservable, right. So, what this one is telling you is, here this observable corresponds to the folded state of the protein, because at lower temperature what will happen? The protein is essentially stable, right. When you go to high temperature, so this high temperature corresponds to unfolded state. See, what have you done? What have you done is, you have started from here, essentially here, right. There the protein was in the most stable form, that is the native form of the protein. Okay. So, this is, I can write the native form of the protein. When you go on increasing temperature, initially what you see is the increase is not that much, but after you cross a certain temperature, say in this case 40, what you see, that change is huge, right. Then after you reach about say 60 for ribonuclease A or 80 for myoglobin, here you can again see this is your denatured form. That means, you have managed to unfold the protein based on the temperature variation you have done. So, what is this observable track? This observable is that observable which changes when you change the temperature of the protein, and because you are changing the temperature, what is changing? The protein is starting from the native state at the lower temperatures and it is going to the unfolded state, and you are monitoring that change using the observable Y. So, this is called a thermal induced transition or heat induced denaturation or a thermal transition. So, thermal transition means a transition which is affected by change in temperature, and that transition is from what? The native or stable state of a protein to the unfolded state of the protein, because you are supplying huge amounts of energy and you are breaking the stabilizing forces within the protein itself. Okay. So, this essentially if you think about it, I can say this part is your transition, because that is where the maximum change is occurring. Now, you can understand the relevance of Tm. What is Tm? Remember, I told something before, it was Tg prime. What was it? It was a cold denaturation midpoint. Why did I say it was a midpoint? Because your Tg and Tg prime, they refer to the midpoint of your transition, and hence this is your midpoint, this is your midpoint, this is your midpoint. So, that is why from now onwards we will replace Tg by Tm, both having the same meaning. There in that case G, why did it we take Tg? Because we took Tg because delta G was 0. Now, we replace it by the thermal melting midpoint and we say Tm. Okay. There is one more important thing to observe in this figure. You look at ribonuclease A and you look at the other protein, which is apomyoglobin. Which one has a higher Tm? Apomyoglobin has a higher Tm. What does it mean? Well, what it means very simply is that the temperature at which you have K equilibrium is equal to 1 for apomyoglobin, that means equal concentration of folded and unfolded, is higher than that of ribonuclease. So, possibly because of this, maybe ribonuclease is less stable than apomyoglobin, or apomyoglobin is possibly more stable than ribonuclease, because Tm by definition is that point where the concentration of folded and the concentration of unfolded are equal to each other, right. K equivalent is equal to 1, delta G is equal to 0. Now, there is one more issue. Have you heard of the word cooperativity? Have you heard of the word cooperativity when you are doing your biochemistry courses? Tell me, based on this or based on your definition of cooperativity, which one of these proteins is more cooperative in its behavior? Ribonuclease A, right. What does it mean by cooperativity? What it means by cooperativity, you open one, everything else gets opened, and this cooperativity is typically determined by the suddenness of the change in transition, right. So, this is the other important point which you can interpret about on this figure or based on this figure. Okay. And then we are going to look at thermodynamics anyway, but these are some very, when you look at a figure, that is why people say that a figure is worth 1000 words. When you look at a figure, you can make a lot more interpretations, because it is just the figure, it is experimental data, it tells you so many things. And it says where Tm is the thermal denaturation midpoint, which we already know. Okay. So, there are 3 regions what we saw. The 3 regions are, one is the pre-transition region. What do you mean by the pre-transition region? If this is the transition, anything before the transition is a pre-transition. Okay. Now, what is the transition from? The transition is from the folded state to the unfolded state. So, if you are talking about a pre-transition, that means before the transition occurs from the folded to the unfolded. So, pre-transition is essentially that belonging to the folded state, right. Okay. Then, so that is what it says, how the physical parameter y, which is the observable y, for the native folded protein varies as a function of temperature. But look at one thing, if you see this, if you see this area, okay, if you see this area, I can say this is typically my pre-transition period or the pre-transition region. But do not you see one thing, that see even this pre-transition where it is mostly folded protein, your baseline, that means your transition is not actually parallel to the x axis. Instead, what does it do? It actually depends upon temperature. That means, even your pre-transition baseline has a slight temperature dependence. That means, if you are going to model it, you have to make sure that when I do a pre-transition modeling of the, because the transition region also is also composed of the pre-transition, that I also better model the pre-transition baseline as a function of temperature. Okay, that is one, right. Let us look at the next slide, sorry, the next point. Next is the transition region. The transition region shows how y varies as the protein unfolds, because in the pre-transition region your y was essentially yn, it was not varying that much, it was varying little based on temperature, but now your transition region is where the maximum change is happening, right. So, this is the transition where the maximum change is happening. Okay. And then you have the post transition region. Obviously, the post transition region shows variation y for the folded protein, where, so it should not be the folded protein, it should be what? it should be unfolded protein. Let me write as I think we wrote this as D, right, and this would be unfolded, sorry for the mistake. So, the post transition region shows once you have done the transition, you have gone to the denatured state or the unfolded state. So, that baseline, which is called the post transition baseline, is belonging to the denatured state. Even that also, if you remember, shows a slight dependence on temperature. See, it shows a slight dependence on temperature, it is not exactly parallel to the x axis. So, that also has to be modeled. So, that is what the last point says. The observed signals for the fully native and denatured states are also dependent on temperature, and this results in baselines with well defined slopes. Slopes means slopes depending upon, that means this signal y n or y d depends upon temperature. Okay. Stop here, I have run out of time. So, tomorrow what we will do is, now we know what a transition is, what a TM is, we will start looking into the thermodynamics of this transition. That means, if you are measuring this transition, how would you fit this transition? That means, you fit this curve to get thermodynamic parameters, because this is finally the ones you are looking for, your delta Cp or delta H, these are the ones you are looking for. So, that is where we are going to start from tomorrow. Okay.